This should be the second video you are viewing related to the special senses vision, our eye. We talked about in the first video how wavelengths of light are able to be separated. They reflect off things, are absorbed by pigments, or reflected if there is no pigment for a specific wavelength of light. And those wavelengths travel into our eye, allowing us to see color and see 3D objects. We also talked about the layers of the eye, the fibrous, vascular, and sensory tunics, or layers. And this is the slide that we left off on, looking at the sclera, the tough white outer part of the eye. We also spoke of the cornea, the clear part of the eye, and how the cornea can become clouded over the course of aging and denaturing, so to speak. And we spoke of cataracts and cataract surgery. And this brings us to the vascular layer of the eye. The vascular layer of the eye, when you hear the term vascular, we should be thinking something related to blood, something related to oxygen. And the vascular layer has functions related just to that. Provides a blood supply to the eye, but it also controls the shape of the iris and the amount of light that is able to enter the eye. We will elaborate more on each of these three functions kind of on the next few slides here. So to first start, the parts of the vascular layer include both the choroid and ciliary body. So let's look first at the choroid. Inside of our eye, when you cut these eyes open, you're going to see a very, very, very black layer to the inner part of the eye. And it's going to look like film. And you can kind of peel it back from the eye. The black part, it is the choroid. Now, when we think about colors and wavelengths, what we need to understand is that there are colors. There's white, there's black, and you may have heard black being the absence of color. Black is no color. Well, here's why black is considered to be no color. The color black contains all the pigments for all wavelengths of light. Therefore, all wavelengths of light are reflected into any object that we perceive as being black. As a result, technically speaking, no light is reflected off something that is black. Therefore, since no light is reflecting off of it, no light is reflecting off of it. And if no light is reflecting off of it, no color is reflecting off of it. And if no color is reflecting off of that object, then there is no color to something black. So what we see on the screen right here, that is technically considered to be colorless. In contrast, something that is white, like this part of the screen over here, it contains every pigment, or no pigment at all. I'm sorry, no pigment at all. So every color of light hits something that's white, and every color of light is reflected back off of it. So every color of light from the sun, it's hitting this part of the screen, and it's being reflected off of it, and all that light goes into my eye, allowing me to see every single color of light. Going back to the first video, I had described sunlight as having a white color, and this is exactly why I say sunlight is white in color. It's because when it hits something that has no pigment, it reflects off it, and I see white. So I would say that the sunlight has a white color. So where are we going with this, and how does this relate to the choroid? Well, first, consider a hot summer day here in Phoenix, right? If you were to go outside and you had to, do some yard work, or maybe you have a summer job where you work outside, what color shirt is recommended that you wear? Something that's black or something that's light in color? Well, something that's light in color, obviously, but why is that? Well, if you think about it, pigments, they absorb light, right? And sunlight is energy. So if you're wearing a shirt that's black, it's going to heat up quicker and stay hot, get hotter, because it's absorbing a lot of the sunlight and a lot of the energy from the sun, making the person's body technically, supposedly feel warmer. Whereas something that's light in color, it's reflecting a lot of that energy off of it and not absorbing as much, allowing it to stay cooler. However, 120 degrees is 120 degrees. I don't know that it makes that much of a difference. But then again, I'm not a person that works outside in the summer. So how does this relate to the choroid now? Well, the choroid, we said, is very black and it's inside the eye. And we do need to understand that light is going through the cornea, through the lens, and into our eye. The purpose of the lens we know is to magnify objects, but really the purpose of the lens is to, like a magnifying glass, direct where the light goes once it enters the eye. Now, if you've ever fried an ant with a magnifying glass when you were younger, you know that by angling the magnifying glass, you can direct a lot of energy to one specific spot, so much so that it actually starts fire. We used to burn leaves when I was a younger kid, we'd start fires with leaves. So the lens, it takes all the light that goes in and it directs it to one spot on the back of our eyeball. Back here, this would be where the retina would be located. The retina is the spot that can actually change light into a visual image. So if we want the light to all go right back here to this one spot, that means the light going in through here, it's going to go to that spot. The light coming from up here, it's going to go down to that spot. Light coming through right here, it's going to go to that spot. But what happens if light were to be, say, misdirected? If it were to go from here and then off to the side of the eye over here, or up here, or down here, and it were not black, the light would be reflected off of it, right? Because there's no pigment to absorb it. What would happen to our eyes then? Well, the light would literally start bouncing around our eyes, which would be intense. It would be insane to imagine what that would even feel like if your eyeball was essentially a house of mirrors for light. So the choroid, essentially, it absorbs stray light rays that were supposed to go to the retina but did not, so that they do not reflect off and bounce around. In essence, the purpose of the choroid is to enhance our vision by absorbing these stray light rays. Now we see the term melanin up here. Melanin is a term we heard before. Melanin was found in hair, or at least variations of melanin were. It's also found in skin. Melanin is the exact same pigment that makes up the choroid of our eye. And this type of melanin, it's produced in heavy concentration. I don't know that I've seen anything blacker in my life than the choroid. Also, the choroid, this area, you would find blood vessels. We can kind of see some in the eyes right here to nourish the living cells that make up the eyeball. The second part that was mentioned was the ciliary body, which consists of two things, a muscle and ligaments. We kind of saw this in this image right here with the real eye. We can see the lens, and then we can see these stringy looking things. And in this drawn image, it's maybe actually not as great. So the ligaments would be what's in white attached to the lens on the top and bottom. It actually goes all the way around the eye, as well as the muscle. So we have the muscle, which attaches to the ligament, and the ligament attaches to the lens. We use the ciliary body to help focus. Now, the lens here, it's not a stationary object in our eye, just like I was talking about a short while ago, where I was able to change the magnifying glass to direct sunlight to actually start a leaf on fire. We can change the shape of our lens, and we do that every time we squint. So when we squint, what we're actually doing is we're trying to see better. How does that work? When we squint, we're kind of contracting the ciliary muscles, and those muscles contract. They then pull on these strings, the ligaments, and as a result of the strings being tugged, the strings change the position of this lens a little bit. And if the lens angles up, then we direct light up. If the lens angles down, then we direct light down. Ultimately, what we're doing is we're trying to change the shape of our lens so that light is getting right back here to the retina, specifically at the spot we're just seeing the fovea. The fovea centralis right here is really where we want light to go, as that gives us our sharpest sense of vision, as we'll learn a little bit later. So the ciliary muscle and the ligaments, they kind of work together to create sharp, clear images by changing the position of the lens. Other components of the vascular layer include the iris and the pupil. We spoke about these terms a short while ago in the first video. The iris is the colored part of our eye, and the pupil is this black hole. The pupil, it is colored, or the iris, it is colored, and the iris, it can get larger, it can get smaller. This typically happens depending on what the light situation is in the rooms that we happen to be in, or if we're outdoors. The larger the pupil is, the more light can enter our eye. We looked previously, first semester, when we were looking at the parasympathetic and sympathetic nervous systems, how our bodies go from relaxed states to heightened sense of emergencies, our fight or flight response. When our bodies jump into that fight or flight response, our pupils here, they get really, really big. So our iris, it actually opens up, allowing the pupil to appear larger, allowing more light into our eye. Well, in a normal situation, when we're not in that fight or flight response, when do we want the pupil large and when do we want this hole small? Well, if you're outside in summer here and it's very, very bright, you really don't need a lot of light entering your eye. So the pupil, it will shrink up. You'll have a tiny little hole in your eye because a lot of light is present and a lot of light is still getting into your eye despite that hole being small. So in bright situations, the pupil is small, but when we go into more dim situations, our pupils will get larger because our iris will open up to accommodate that loss of light to let more of the light that still is present into our eye. When we go to dissect our eye, you would actually see lines kind of in our eye that kind of function similar to like maybe an accordion, if you will, opening and closing kind of to allow for size. And once again, when I say the pupil is a hole, literally, there's literally nothing right where my mouse cursor is. There's nothing there. It is a hole. We will stop this video here, and in our third video, we will start looking at the nervous layer and color.